flexibility into the schedule. All right, well, what I want to say today is, let's see, make sure I've got my camera on here. I forgot to do my usual last-minute check. Yes. Okay. So what I want to do today is finish up talking about carbohydrates in general, and then we're going to start talking about the metabolism of carbohydrates. And somebody asked me before class about, well, you know, what happens when I'm making ATP if I am exercising, not exercising? What are the different considerations of that? And that's what we're really getting ready to get into. And that's the exciting stuff of metabolism. After we talk about some of that stuff, I think, and certainly I hope, that you'll have a much better understanding about how your body works. Really important to have that perspective, and especially as budding nutritionists and budding food science students, that I think this is important for you to understand. So that's coming. Why is that doing that? Okay, so last time I finished talking about the various projections. Those were the Haworth projections that I talked about, and I briefly mentioned the chair conformation, and I said that we could bend these bonds and have a boat conformation, and when we get in the boat, things don't always fit quite as nicely. So there are some sterical, what we call steric constraints, that is spatial constraints of atoms that don't like to be scrunched too close together. And so that affects the overall structures that molecules have. Well, I want to spend a little bit of time talking about some of the chemistry of sugars. And this actually relates to things in food, all right? So chemistry of sugars. This shows something important about sugars, all right? So I described two basic categories of sugars, aldoses and ketoses. An aldose was something that had an aldehyde group at the end, and a ketose was something that had a ketone at the end. I said glucose was a good example of an aldose. Fructose was a good example of a ketose. Okay? And I pointed out or reminded you of your organic chemistry that aldehydes tend to be more reactive than ketones do. And consequently, glucose turns out to be more reactive than fructose is. All right? Now, as we will see, the stuff that we sweeten our drinks with is are primarily either sucrose, which is a combination of glucose and fructose, or fructose, as in high fructose corn syrup. One of the reasons that high fructose corn syrup is very popular among food manufacturers is because fructose is fairly stable. Sweetening things with glucose by itself isn't as practical as it is sweetening things with fructose. Okay? Fructose also tends to taste a little sweeter, and that makes a difference as well. Well, these things all relate to something that you see on the screen. And specifically on the screen, if I were to show you this, I would hope that you would look at this and you would say, oh, that must have been, this sugar was an aldose. How did I know that? Well, I knew that by virtue of the fact that carbon number 1 was the one that connected to the oxygen. When I showed the cyclization yesterday, you saw carbon number 1 of glucose connecting to that oxygen. It turns out that when a ketose cyclizes, it's carbon number 2 that does that. So looking at this, you'd say, well, carbon number 1 connected, so this had to have been an aldose. Okay? Aldoses are more reactive than ketoses. Okay? And so aldoses can, in fact, be oxidized very readily. They can be oxidized. So we talked about oxidation and reduction, and aldose can be oxidized. When you oxidize an aldose, you produce an acid. Okay? We don't even need to worry about what the acid is, but you oxidize an aldose, you produce an acid. Well, remember I said that when something gets oxidized, something else must get reduced. Okay? So a sugar that readily gets oxidized is called a reducing sugar because it's reducing something else. So as it's getting oxidized, it's transferring its electrons to something else, which is getting reduced. So in general, we will say that aldoses are more reducing sugars than are ketoses, because we can more readily oxidize an aldose than we can a ketose. Okay? We can also take a sugar to the laboratory and we can reduce a sugar. That is, instead of oxidizing it, we can reduce a sugar by adding appropriate chemical treatment of that. And if we do that, we create something called an alditol. Okay? Most of you have probably heard of sorbitol, right? Sorbitol is used as an artificial sweetener, and it's used as an artificial sweetener because it turns out that we don't metabolize it very well. But it has the same basic structure or elementary structure that the sugars we've talked about, fructose and glucose, have. So the body gets a little confused. Body says, oh, yep, I've got fructose or glucose, so I'm going to signal to my brain I've tasted this, which means the brain says, something sweet. And the rest of the body says, well, this isn't the structure that I am normally used to metabolizing. I don't know what to do with it. And so instead of getting all that energy out of it, which is what we get if we eat sugar and metabolize it, this sort of passes through the system. So an alditol, which is a reduced sugar, not a reducing sugar, a reduced sugar like sorbitol. Sorbitol is a specific type of alditol. Okay? Alditol is a category. Sorbitol is a specific type of alditol. Right? This functions then as an artificial sweetener. Okay. In addition to other chemistry, sugars can also get what we call phosphorylated, meaning that a phosphate can be put onto them. A phosphate can be put onto them. When we talk about glycolysis, either later today or early on Friday, we will see that the very first reaction that the body does to glucose is to put a phosphate onto it. That's exactly what you see on this screen right here. There's glucose. There is ATP. The ATP is a source of energy, and the ATP is also a source of phosphate. Two birds, one stone. Okay? In the reaction, the very first reaction of glycolysis, the phosphate is transferred from ATP onto glucose. It makes something called glucose 6-phosphate. We'll talk about that later. Okay? So sugars with phosphates on them are very common throughout all of our cells. Okay? Another kind of chemical reaction that can happen to sugars is to make what are called glycosides. Glycoside. All right? How do I make a glycoside? All right? Well, I make a glycoside. In fact, I need to actually tell you another nomenclature word that I didn't give you the other day that you should know. Remember I said we took and we made those Haworth structures, we made a ring? Okay? And I said when we made that ring that we created a new anomeric carbon that could be in the alpha or the beta configuration. Okay? That carbon, that newly asymmetric carbon that we created, is known as the anomeric carbon. A-N-O-M-E-R-I-C. The anomeric carbon. Okay? So that means that if I'm describing two things that are, if I say two anomers, that would mean two things that differ only in that one is alpha and one is beta. So I could have alpha D-glucose and beta D-glucose. Those two sugars would be anomers of each other because they would differ in the configuration of their anomeric carbon. All right? Well, I tell you that because when I make a glycoside, I'm altering the hydroxyl on that anomeric carbon. Gesundheit. Okay? I'm altering the hydroxyl on the anomeric carbon in making a glycoside. That's what you see on the screen. There's the anomeric carbon because it's the one that's attached to the oxygen. You can see that in this case I'm adding a methyl group to it, so instead of having an OH, I have an OCH3. That creates a glycoside. Okay? Now, once I create a glycoside, this structure will always stay in that same beta configuration. This guy here can flip alpha to beta to alpha to beta to alpha to beta in water. Okay? But this guy will always be stuck in the beta if I did it in this. Or if I started and put the methyl on it when it was in the alpha, it would be stuck in the alpha. So whatever configuration the anomeric hydroxyl is in when I alter it, it will then stay stuck in that configuration. If I don't alter it, it can flip from alpha to beta and back. Okay. Now, this turns out to be important because if you looked at the nucleotides, for example, the nucleotides had a sugar, they had a phosphate, and they had at least one phosphate, and they had a base. The base got attached onto the anomeric carbon. That meant that it was always in the up position. And that's important because we have to have consistency in the structures of our nucleotides in our DNA. Okay. Here is another glycoside. All right. There's the OH, or what was the OH, and it's been altered, as you can see. It's drawn this sort of side configuration because it means sometimes it can be in the beta, sometimes it can be in the alpha, but whichever one it's put into, it's stuck there. It's not switching back and forth between them. Laetrile is a toxic compound that's found in apricot pits. Some people think it has anti-cancer properties. Other people say any poison has anti-cancer properties. Cyanide has anti-cancer properties. Okay? All right. So some other things we need to think about are some other terms I talked about. So far I've been talking about simple sugars, meaning that we only had one sugar comprising a compound that we're talking about. We start moving our consideration now to what are called disaccharides. Disaccharides have two sugars linked to each other. Okay? They usually are linked by at least one glycosidic bond. Right? Meaning that we've made a glycoside. We altered the hydroxyl of at least one anomeric carbon. Well, here is a structure down, down, up, down, up. This is a glucose, down, down, up, down, up. That's a glucose. These are two glucoses that have been linked to each other by what's called an alpha 1,4 configuration. Don't worry about that at the moment. All right? But the point I want to make is that this alpha was originally an OH, and it's been replaced by this other sugar. It means I've made a glycoside. Okay? Notice at this end, I still have an anomeric hydroxyl. This guy, once it's made, can't flip. This guy over here can flip. Okay? All right. Now, I talk about disaccharides because some of the disaccharides are very important. That's a very high-quality figure I drew myself. I bet you guys never would have guessed that, would you? Right? The reason I drew it myself is almost every book on the face of the earth draws sucrose in a really stupid way. And they draw it stupid because they put the two sugars side by side, and the student has to look at it and do mental gymnastics. And I prefer not to do it. This is actually the way sucrose looks. Okay? So let me show you what's in sucrose so you can better understand it. Oh, and by the way, I forgot to mention this also. Your book doesn't have structures, which is the book I wrote. Your book doesn't have structures of fructose in it. I discovered that later. So I have various structures. There's a structure of fructose, and there's a structure of ribose that you should, those are things that you're responsible for. Okay? So you can pull those out of there. Anyway, I want to show you the structure of sucrose because sucrose turns out to be an interesting molecule. It's interesting because there's a glucose here. The glucose is linked in an alpha configuration. That means the OH was down. And it's linked to a fructose in which the anomeric hydroxyl was in the beta or up position. Okay? Well, what this meant was that sucrose is actually a diglycoside. Both of the anomerics are connected to each other. Okay, that's not very common. Not very common at all. But they're connected to each other. And it turns out that the most reactive parts of these guys are the anomeric carbons. When I talked about the reducing sugar and I said that glucose got oxidized, the thing that was getting oxidized was that carbon number 1, that anomeric carbon. If fructose gets oxidized, its carbon number 2, which is this guy, the anomeric carbon here, gets oxidized. Okay? So by connecting the two anomeric carbons to each other, it actually stabilizes the structure, meaning it's less likely to get oxidized. So sucrose is actually a stabler form of these two sugars. Probably one of the reasons that plants and other organisms make it, because it's fairly stable. Stable things you can have around for a while. Okay. All right. That is the structure of sucrose. All right. Another relevant, and this shows several other relevant disaccharides. I'm not going to ask you to draw the disaccharides, okay, so don't sweat that. But I think you should know what are in them. You should know, for example, that sucrose has fructose and it has glucose, and they're linked by two glycosidic, two anomeric carbons joined to each other. Some other disaccharides that we hear about are lactose. Okay? Lactose contains glucose and galactose. And you can see this only has one anomeric carbon. That's the one right here that's tied up. The other one is free. Okay? The other one is free. Right? So lactose is not like sucrose. We would expect that lactose would not be as stable as sucrose, and it's not. It would be more reactive than sucrose would be. Lactose is also known as milk sugar because it's the sugar that's found in milk. And we hear about lactose intolerance. What does lactose intolerance mean? Lactose intolerance means that we lack, or some people lack, enough enzyme to break down lactose. Normally when you drink milk, dairy products and so forth, which have lactose in them, you have an enzyme that breaks down lactose into its simple sugars, galactose and glucose. And once you've broken it down into those simple sugars, your body absorbs them and you use them. If you lack that enzyme, and by the way, the enzyme that breaks down lactose has a very simple name. It's called lactase, Lactase. If you lack lactase, or you don't make enough lactase, which happens in many people, especially as they get older, then lactose doesn't get broken down. And instead of you absorbing the galactose and glucose, the lactose stays in your digestive system, and your digestive system is crawling with a few trillion bacteria that look at this and say, yum, yum, I'm going to activate my lactoperon. Remember? And I activate my lactoperon, I can break this down, and when I break this down, boy, I can sure produce a lot of gas. And that's what they do. So people who have lactose intolerance usually will have production of a lot of gas, and probably more relevant to them is they have a lot of pain associated with that. So lactose intolerance can be very, very painful, and it's because they're not making enough of the enzyme lactase. Other disaccharides include cellulose, maltose, and isomaltose, and I won't say anything more about those. Okay. When we talk about sweeteners, we also frequently talk about artificial sweeteners. And one of the most common questions I get from my lectures on carbohydrates are, what about artificial sweeteners? What do you think about those? That's what I'm asked about those. So I always like to tell this story to students with respect to artificial sweeteners. Okay? So this is a compound called sucralose. And sucralose is an artificial sweetener that bills itself. It's just like sugar because it's made from sugar. Okay? So therefore, the implication is it's safer for you. Well, I don't know offhand of anything about sucralose that's unsafe for you. Okay? So that's my first answer to students. It doesn't mean I'd go out and I'd eat a pound of it every day. but I don't know of any evidence that sucralose is harmful to you. But I will tell you a little bit about how the structure of sucralose, or how sucralose was made originally. Maybe some of you have heard this story. The story is as follows. The people who first synthesized sucralose were not trying to make an artificial sweetener. They were trying to make an insecticide. Okay? They were trying to make an insecticide because these carbon-chlorine bonds are not something that we typically see in biology. And when we see bonds like that, they're in compounds that we know are fairly toxic. They include things like dioxin and similar compounds. So the idea was if we made some carbon-chlorine bonds that we fed to insects and we got them to eat it and they couldn't metabolize it, they would die from these compounds. That was what they were trying to do originally. And they made this in a laboratory in England. Okay? And in this laboratory in England, they finished the synthesis. The professor finished the synthesis, okay? And he left a phone message for his graduate student that said, test it, and we'll know more about this on Monday. And the graduate student thought the message said, taste it. And he did. And when he came in on Monday, he told the professor, it's sweet. And the professor says, what in the hell are you talking about? And he said, you said taste it. And he said, I said test it, you idiot. Now, I don't know if that's urban legend or not. Okay? I do know that carbon-chlorine bonds are probably something I don't like to mess with. Okay? So the impetus for making this was not making some artificial sweetener. It was for making an insecticide. Okay? A little bit disturbing, right? So, as I said, I don't know of anything that indicates sucralose is poisonous, but in fact, I won't use it. So let's put it that way. All right. We move from disaccharides to talking about polysaccharides. Polysaccharides, as the name suggests, are things that have many sugars. And perhaps before I even say anything about polysaccharides, I should say there is something in between disaccharides and polysaccharides. I'll say a little bit about them at the very end of the lecture, and they're called oligosaccharides. That is, they have a few sugars joined to each other. Well, polysaccharides are basically storage forms of sugars, polysaccharides. What you see on the screen is a common polysaccharide we find in plants. It's known as amylose. And it's a polymer of glucose. The glucose units are joined by what we call alpha 1,4 bonds. There's the position number 1, and there's position number 4. The position number 1 is in the alpha, so we call it an alpha 1,4 bond, alpha 1,4 bond, and you'll notice down here it says 300 to 600 of them. We may have 300 to 600 of these guys, all glucoses, all in alpha 1,4 bonds. Plants use this as a way of storing glucose for energy. And we look at that and go, yum, yum. Plant energy is good energy for me, and we can eat this. And our digestive system will take this and will readily break it down. We have an enzyme in our saliva, for example, called alpha amylase, which will take and start the breakdown process of this as soon as we put it in our mouth. Okay? So the digestive system is set up very nicely to handle compounds like this. Okay? Another related set of compounds from alpha amylose is something called starch. Okay? Starch really isn't one thing. It's a mixture of things. One of the things that it is, one of the things we find in starch is amylose, alpha amylose, just like I told you about. The other thing we find in starch is something called amylopectin. And it's related to amylose, but it's not the same thing. How does it differ? Well, if we look at amylopectin, we see, if we look along the bottom line right here in the bottom, we see alpha 1,4, alpha 1,4, alpha 1,4, alpha 1,4, alpha 1,4. Everything there is like amylose. If we look at the top line up here, we would also see alpha 1,4, alpha 1,4, alpha 1,4, alpha 1,4. Most of amylopectin looks just like amylose, the difference being that we see a branch. We don't see any branches up here. The branch that we see is every now and then there'll be a new chain that'll be linked in an alpha 1,6. That's position 6 configuration. So alpha 1,6s are branches, and they produce, whenever we see them, they produce amylopectin. These branches in amylopectin occur about every 50 to 100 residues. That is, every 50 to 100 sugars, we'll see a branch. Now, I give you that number because we have a very similar compound in our body known as glycogen. But instead of having branches every 50 to 100, we have branches about every 10 to 30. There's a reason why, and I'll tell you that later. But suffice it to say that our glycogen is very much like a plant's amylopectin. Just has a lot more branches. A lot more branches. Everything I've shown you so far is a polymer of glucose. Here's glycogen. Okay? Not a very good figure, but there's glycogen showing you the branch points. Every 10 or so residues, we have one of these alpha 1,6s. And again, this will have a new branch, and then it goes alpha 1,4, 1,4, 1,4 until it gets to another branch and an alpha 1,6. Okay? That's what our glycogen looks like, and it's just simply more branched. Polymers of glucose. These are ways of storing glucose. We store glucose in our body primarily in our liver and in our muscles. That's the two primary places we store glycogen, because glycogen is a source of glucose, and glucose is a source of energy. The liver, as we shall see, plays a very important role in controlling the level of glucose we have in our blood. So we can think of the glycogen as a storage, and when the body needs glucose, the liver breaks down glycogen and releases it into the bloodstream. Okay? When our blood glucose is too high, our liver will take up the glucose and store it as glycogen. So we see a back and forth with this. And that's very important because, as I've said before, and I said I would bore you with this, glucose, as we will see, is a poison. Glucose is a poison. All right. Well, there's one more glucose polymer I want to talk about, and that's cellulose. And though that is drawn a little bit differently, in fact, cellulose is very, 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 very similar to alpha amylose. Alpha amylose, you remember, was the polymer that was just linear, and it was alpha 1,4 glucose, no branches, no nothing else. Cellulose is also a polymer of glucoses, no branches, no anything else. But instead of being alpha 1,4, it's beta 1,4. So that anomeric carbon is pointed up instead of pointed down. That simple difference has giant implications. We have alpha amylase that can break down amylose. We can break down amylopectin. Okay? We cannot break down cellulose. We do not have the enzyme that's necessary to break down cellulose. When we eat cellulose, it passes through our system and gives rise to what we call roughage, because we can't mess with it. We can't break it down. Okay? Organisms that can break down cellulose include ruminants, like cows. Cows also don't have an enzyme to break down cellulose, so how in the H do they do it? They do it because their rumen contains a bacterium that has that enzyme. The enzyme, again, a simple name, is called cellulase. So cellulase breaks down cellulose, and that's why you see cattle eating grass, because grass is, of course, full of cellulose. Cellulose is a primary component of plant cell walls. When we eat lettuce, right, we get a little bit of the nutrients from lettuce, but a lot of the lettuce we can't mess with the cellulose that's in there. All right? A cow can. A cow can do that. A cow is deriving a lot of energy, a heck of a lot more energy than we are, from the plants that it's eating. Okay? So grass, various things like grass and so forth that ruminants eat are giving them energy. Okay. That's sort of a schematic that compares amylopectin, not too many branches, with glycogen, a lot more branches. The reason that branches are important is due to the way that we metabolize glycogen. I said that we use glycogen as a storage mechanism for us to release glucose as we need it from our liver, or to release it as we need it in our muscles, because our muscles use glucose for energy to do what we do. All right? Glycogen is metabolized by starting at the end and chewing inwards. Enzymes that break down glycogen do that. They start at the end and they chew inwards, one at a time. We'll talk about those in a little bit. All right? Well, if you think about it, the more ends you have, the more you can break down glycogen into glucose more rapidly. And animals need to do that because animals have muscles. Animals need to run. They need to escape prey, escape predators. They need to catch prey, whatever it is that they're doing, right? They need to do quick energy. More ends, more glucose, more quick energy. Plants don't run away from anything. They're kind of sedentary. They don't need quick energy. They don't need as many ends. And in fact, that's one of the reasons they make amylose, which only has 2 ends. Right? They don't need to break it down very rapidly. We need to do that. So glycogen structure makes a lot of sense. Okay. The last things, so I want to talk about one polymer that's not a polymer of glucose. Okay. This is called chitin. Anybody know what chitin is? What's chitin? Exoskeleton of insects, for example, is a polymer of this thing right here, N-acetylglucosamine. If we look at this, here's glucose. It's glucose in the beta configuration, but we see carbon number 2 has been altered. That's the N-acetyl part. Okay? And the rest of it looks just like glucose. If you take this altered compound and you make a polymer of it in the beta 1,4 configuration, you make something called chitin. Okay, that's the exoskeleton of insects, and that's strong and sturdy, kind of like cellulose is for plants. Kind of like cellulose is for plants. Okay. There are other polymers that I won't go through here. All right. The last things I want to talk about, excuse me, are glycoproteins. Okay. Glycoproteins come in a couple different forms. One, something called a proteoglycan, which sounds like I've just turned the name upside down, but it's actually named that for a reason. Okay? A glycan is a polymer of a sugar. So, for example, we could say that amylose is a glycan, right? It's a polymer of a sugar, right? A proteoglycan means that that sugar polymer is attached to a protein. So proteoglycan has a polymer of a sugar, or polymer of many sugars, attached to a protein. Excuse me. Typically, the sugars that are polymers are actually altered sugars. They're chemically altered. They're not glucose. In fact, they're usually sugars that have negative charges on them. Negative charges. So here is a polymer of hundreds or thousands of sugars. Every single sugar in there is negatively charged. What happens if I try to put something that's got thousands of negative charges here next to something that's got thousands of negative charges right there? What's going to happen? They're going to repel the hell out of each other, right? these long polymers of negative charges give rise to some interesting properties. Okay? They repel each other, and they really alter the chemistry of the water that they're dissolved in, because that's where we find them. Okay? They repel each other, and they spread each other out. They really make the thing a more of a globby type of structure, and they give the feeling of being slippery. They're very, very slippery compounds. Your snot, for example, is loaded with this kind of stuff. Next time you play with your snot, you can think about that, right? Mucus is full of that stuff. All right? Other things that are full of that kind of stuff are the synovial fluid of your joints. Synovial fluid is a lubricant that helps your joint, keeps your joints from rubbing in, the bones from rubbing into each other. And as you get older and you stop making less synovial fluid, what happens is this part starts rubbing on this part, and people will develop a lot of pain. Okay? Synovial fluid is a lubricant that prevents that from happening, and it's that slippery nature that I'm talking about. This is one of the components of the synovial fluid. It's called hyaluronic acid. And it has a structure that's kind of like what you see up here. Okay? Long polymers of these negative charges that are giving a slippery component to it. And these things are very, very effective at acting as lubricants. They have other properties that they possess as well. Okay. Well, the last thing I wanted to say was actually, I promised I would say something about oligosaccharides. And I saved it till the end because oligosaccharides we don't usually find by themselves. They're usually linked to proteins also. But instead of being a proteoglycan where we have a long polymer of these, hundreds of these, thousands of these, oligosaccharides are only, let's say, less than 10. 3 to 10 sugars attached to a protein. We call these glycoproteins. That's the simple name that we give them. Okay? And this figure right here shows something about what an oligosaccharide looks like that is in our blood. So oligosaccharides on proteins in our blood have an identity marker. That is, they have a specific structure. I didn't draw the structure. I just give you the names of the sugars that are linked to each other. And that structure here is different than that structure here. So if I possess this structure on my glycoproteins on my blood cells, I have type A blood. And if I possess this structure on my blood cells, what's the difference? The difference being right here compared to right here. Okay. Then I have type B blood. Okay? So what I'm telling you is that the different structures of the oligosaccharides on my blood glycoproteins determines my blood type. Yes, question? Okay. So O is another one that has another distinctive structure. I didn't show it on here. But O would also have a distinctive structure. Now, plus and minus factor have other considerations. Okay, it's called the rhesus factor, and I won't the RH factor. I won't go into that here. But the simple blood types O, A, AB, etc., arise from this. And the reason that we can't mix many of these types is because our immune system is set up to recognize them as foreign, and they will attack them. So if I try to give a person who's got type A blood, type B blood, the immune system says, you're an A. Whatever is in here is foreign. I attack it, and it can be fatal. Okay? O negative is what's known as the universal donor. Okay? Because it doesn't have any specific thing that activates the immune system. So I can put O negative blood into a patient and not have the consequences that I have if I were to try to put an A into a B, for example. Does that make sense? Clear as mud? But the important point here is that the oligosaccharides on those blood glycoproteins are what give rise to the different blood types. Okay. Well, I think before starting glycolysis, and yes, I'm going to start glycolysis today, we should do a song to reinforce what we've learned. And the song is very simple. It's a very easy song to learn, a very simple song to sing. It's called Hark the Sucrose. It goes, carbohydrates all should sing, glory to the Hayworth ring. Anomeric carbons hide when they're in a glycoside. Glucopyranose is there in the boat or in the chair. Alpha, beta, D, and L, diastereomer hell. Alpha, beta, D, and L, diastereomer hell. Okay. Now you've learned your sugars. Right? All right. To me, we're getting to the most interesting part of the term. Okay? I love talking about metabolism. I really love talking about metabolism. Because it's with metabolism that I find talking to students, they say, wow, this is why biochemistry is cool. And most students tell me they come into metabolism going, oh my God, I'm going to have to learn all these pathways. All right? So it's one of the reasons I don't make you memorize an awful lot of things out of pathways. There are some things, yes, I'm going to make you memorize. Okay? But the take-home message of these pathways is how do they give rise to the phenomena that you associate with how your body acts? Right? How do they give rise to that? And you're going to see that by understanding metabolism. Okay? So glycolysis is something we call a central metabolic pathway. There's a term for you. A central metabolic pathway. And a central metabolic pathway is called that because if we look across all of the cells on the face of the earth, this pathway, first of all, will occur in almost every one of them. And we'll see that things from this pathway relate to other pathways. So we're getting ready to talk about the process of metabolism. And the process of metabolism, people draw analogies to highways. To highways. Metabolism means that molecule A is converted into molecule B. And molecule B is converted into molecule C. And molecule C is converted into molecule D, etc., etc. Just like the highways connect towns. So if I go from Corvallis to Portland, I go Corvallis to Albany, to Salem, to Woodburn, to Wilsonville, to Portland, right? Or something like that. Each of those towns could be a molecule in a metabolic pathway. And just like I could go to Portland by going from Corvallis to Albany to Salem, etc., I could just as easily go from Corvallis to Monmouth to Salem to Portland. So I can get somewhere by alternate pathways. And I see that these roads intersect. Okay? We see metabolic pathways intersect as well. I want you to keep in mind that metabolic pathways are man-made inventions. We call a set of 10 reactions glycolysis. But those 10 reactions of glycolysis are mixed in a soup in our cells of thousands of reactions that are going on at the same time in the same place. We've simply said, we're going to call this glycolysis. Okay? You understand? It's like saying we're going to Portland, right? We're going to Portland, but we don't say how we're going to get there. We know that there are hundreds of highways in the state of Oregon, all right? Going to Portland is just one route, one thing that we can do. We could go to Ontario, we could go to La Grande, we could go to Baker City, right? On any of these highways. And these highways are all going on all the time, and we're thinking about the one place that we're going. So the metabolic pathways are like that. We're focusing on one component of something that's happening in chaos in the cell. I want to emphasize that. Okay? A goes to B, goes to C, goes to D, but A can go to B, can go to J, can go to Q, can come back over here and go to L. Are you with me? So I'm telling you there's alternate ways of getting. And any compound that we see in a metabolic pathway may appear in other things we call metabolic pathways. We'll see that the pathways start to connect. Glycolysis, which is the breakdown of glucose, connects to pathways that involve the breakdown of pyruvate. We see that the breakdown of glycogen, one of the products of the breakdown of glycogen you've already seen is glucose. So something we call glycogen metabolism connects to glycolysis. Now that's important because everything that happens in the cell is ultimately connected to everything else in the cell. We think about them in isolation, but they're all connected. Okay, that's a very important first point. Okay, let's start with the big picture. Here's the big picture. We start with glucose. Glycolysis is the breakdown of glucose. If we look at the name, and by the way, I'm a real word person if you guys haven't figured this out already. Glycolysis means glyco, referring to sugar, lysis meaning breakdown. Glycolysis means breakdown of sugar. Glucose is the sugar being broken down, and as I've said, glucose is the most abundant sugar on the face of the earth. Nothing's even close. Okay? Most abundant sugar on the face of the earth. All right? We're breaking down glucose. There are 10 steps in the breakdown of glucose. We define the start of glycolysis as glucose, and we define the endpoint of glycolysis as pyruvate. Notice I said we defined those. All right? You'll see we start with one glucose, and you see down here we get 2 pyruvates. Glucose has 6 carbons in it. Pyruvate has 3 carbons in it, so 2 times 3 equals 6. We haven't lost any carbons. We just converted them into a different form. Okay? There are a series of reactions that are going on here. And yes, I'm going to ask you to know the names of the compounds that are in here. I'm not going to ask you to memorize the structures of the compounds. Okay? Glucose goes to glucose 6-phosphate, goes to fructose 6-phosphate, goes to fructose 1,6-bisphosphate, goes to glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. Goes to glyceraldehyde 3-phosphate, 2 of them. Now we've got 2 glyceraldehyde 3-phosphates, which go to 1,3-bisphosphoglycerate, which goes to 3-phosphoglycerate, produces an ATP, which goes to 2-phosphoglycerate, which goes to PEP, which goes to pyruvate. We are done with glycolysis. 10 steps. I'm an old guy. I can memorize that. You guys can memorize that, can't you? Don't pull that old guy thing on me, guys, right? You guys know better than that. All right? These reactions are actually fairly simple. And you'll notice as I was going through and talking about those names that virtually everything I talked about had the word phosphate associated with it. Okay? This process starts by putting on a phosphate, like I said last time, and we'll see that that phosphate plays an important role all the way through. Okay. I think since I see the shuffling, and I'm one who can pick up the signs reasonably well, it's time to call it a day. So I will see you all on Friday when we'll have a lot of exciting things to say about glycolysis.